Second team up on our docket today is Arizona State University with their concept, AEGIS. Take it away, Arizona.
Awesome. Hello, everybody. We are super excited to be here representing ASU at this year's NASA Big Idea Forum. Before we begin the presentation of AEGIS, the inflatable lunar landing pad, we'd like to give some introductions on who will be presenting to you today. My name is Grant Leslie. I'm a senior studying mechanical engineering, and I'm the team's project lead.
My name is Ellie Arnold. I'm a graduate student studying computer engineering, and I did the systems architecture.
Hi, everyone. My name is Grace Ryder. I'm a senior studying economics and sustainability, and I was responsible for materials acquisition on this project.
Hi, all. My name is Connor Owens. I'm a second-year mechanical engineering major, and I focus on the base anchors.
Hi, my name is Servan Shah. I'm an electrical engineering graduate student, and I worked on the electrical and embedded design on this project.
Hi, everyone. I'm Georgia Lee. I'm a second-year mechanical engineering student, and I worked on materials testing as well as mechanical design.
Hi, guys. My name is Vaibhav Khanna. I'm a graduate student pursuing mechanical engineering. My role was ANSYS simulations and mechanical design.
Awesome. So today we're going to be going over the full project lifecycle of AEGIS, from the initial problem statement defined at the project's onset to an overarching system design and concept of operations. From there, we'll look into a detailed system design along with the manufacturing process used to produce all of our systems and test articles. And then finally, we'll go into our evaluations through relevant environment testing and Earth analog testing to progress AEGIS to TRL 5. Then we'll wrap up with a path to flight to take AEGIS even further.
One of the challenges of creating a sustained lunar presence is safe landings on the lunar surface. The lunar terrain is made up of regolith and has been shown that the fine-grained particles in regolith are prone to creating debris clouds caused by lander exhaust. This regolith can travel at speeds of 2 kilometers per second, potentially damaging nearby landers and equipment. This regolith can even be ejected into orbit, which can possibly damage orbiting spacecraft. This poses a threat to instruments and equipment due to the contamination and abrasion, and it affects the ability for landers to land near each other. The current solution to this problem is to create safety zones around each lander, preventing other vehicles from landing in the vicinity. However, if we want to build a sustained presence on the moon, landers will likely need to land near each other to allow for more collaborative and less costly missions. This is why we are proposing AEGIS as an inflatable landing system to reduce the dust and debris caused by landers. At its core, AEGIS solves this problem by serving as an intermediary surface between lunar regolith and exhaust gases, preventing the propagation of debris clouds. In order to achieve this task, AEGIS has 5 major subsystems. First, we have an enclosure, which constrains all subassemblies together. We have a heat shield, which serves as a barrier and an insulator between critical components and high-temperature exhaust gases. We have an inflated skeleton, which serves to increase the area of coverage 6-fold, as well as develop angle deflectors around the system's circumference. We have a composite tarp, which serves to span and envelop the inflated skeleton, impeding gases from reaching the regolith. And finally, we have an anchoring system located inside of the enclosure, which constricts the system both vertically and laterally. Walking us through our concept of operations, first, a rover would deliver AEGIS to the landing site, where it would deploy the system and drive off. AEGIS has 6 anchors that it will drill into the regolith, securing it in place. Once the system is secure, the panels will release to allow for inflation. As the system inflates, the walls will open and the tarp will unfold until it is taut. AEGIS has 6 main spokes that allow it to inflate to and hold its shape. Once the outer barrier is inflated, the system is fully deployed and ready for a lander. Landers will center onto AEGIS by using a communication system that was descoped for the sake of this proposal at the recommendation of the judges, but would be included in the final system. As the lander approaches, the thrust is forced away, protecting the lander from regolith beneath and around the pad. After the lander touches down, the outer barrier will deflate to allow for payloads to be offloaded. And once everything is offloaded, the outer barrier will reinflate, the lander can take off, and AEGIS will be ready for another lander.
Now that we have an idea of AEGIS' concept of operations, we can move into detailed analysis of each of its subsystems. We'll begin with the enclosure. Seen its stowed configuration in the top left, the enclosure is constructed of 6061 aluminum sheet metal. Located beneath the nested central heat shield is a central housing which encompasses all electronics, compressed gas, and base anchor subassemblies. The exterior panels are spring-loaded and overlapped in such a way that with the use of 6 frangible release nuts located at the tip of each of AEGIS's 6 triangular panels, the outer enclosure can open up, revealing the inner tarp and skeleton. Once revealed, the inner tarp uses compressed nitrogen gas to expand to 6 times its original footprint. This inflation is driven based off an inflated skeleton, which is comprised of 12.7 centimeter diameter inflated Kevlar beams. Once inflated, the full system covers 153 meters squared, which is a 14-meter diameter circle with 0.7 meter deflector lengths and a deflector angle of 32.5 degrees. These geometries were driven through CFD analysis and inflated beam theory to minimize fluid shear stress, which represents the regolith getting kicked up by exhaust gases, as well as compressed gas volume. To further reduce compressed gas volume, check valves have been employed at the inlet to the lower and upper ring, such that reinflation cycles only need cycle out gas from the linear spokes. This results in a final compressed gas volume of 0.21 meters cubed, stored at 15 megapascals.
As Ellie mentioned, the purpose of the tarp is to protect the lander from the lunar regolith. And as you can see from this test article that was built out by our team in-house, it is comprised of aluminized Kapton and alumina felt sandwiched between layers of carbon fiber, all of which is stitched together with a ceramic thread to provide mechanical durability without compromising thermal protection. So the carbon fiber provides mechanical integrity, the alumina felt reduces conductive heat transfer, and the aluminized Kapton minimizes air permeation. This combination of materials was selected to provide structural integrity and thermal insulation while also ensuring flexibility and compactability in housing. And it works with AEGIS's heat shield, which, as you can see from this test article that was also built out in-house, it is comprised of RVC foam and a carbon-carbon composite that's sprayed with a yttria zirconia coating to create an additional thermal barrier. So RVC foam has an operational ceiling of about 3,500 degrees Celsius, which makes it indispensable for protecting the sensitive electronics housed within the AEGIS system, which is the primary purpose of the heat shield. And the carbon-carbon composite's ability to resist thermal degradation at ultra-high temperatures makes it ideal for the exhaust-facing surface of the heat shield.
Next are the anchors. They were designed to support the load in both lateral and vertical systems when a failure case of the left side only inflating with the 3 left anchors out of 6 in the enclosure. A novel deployment system was innovated and implemented with this system. A rectangular shaft travels through the auger, and this rotational motion connected to a motor is then translated into vertical deployment through the threads that along the sheath and at the beginning of the auger. Finishing up this anchor section, we're going to be going into manufacturing with a 1/5 scale. And this is how we brought it from TRL3 to TRL5. With the enclosure, we have on the left a plain aluminum. This was used for preliminary testing. And on the far right is a white powder-coated aluminum. Same thing, but it looks much nicer. And it's used on the final. Well, there was 2 inflatable systems designed. The blue shown here was manufactured and designed in-house using a mechanical clamping system to seal the hoses. And it was made out of vinyl tubing. And on the far right is the final inflatable structure, and that was manufactured by an inflatables company and is made out of PVC. For the tarps, a neat carbon fiber composite was manufactured in-house, and it was used for the thermal testing and the rocket fire testing. And on the far right is the ripstop nylon, and that was used and manufactured in-house is used for the ease of handling and transportation.
Okay, so coming on to the electronics and controls for AEGIS's Earth analog prototype were set up in a distributed manner, which made for a simpler design and allowed us to easily meet the power requirements of the various components involved in the system. So in the top figure, you can see our circuit, and within that figure towards the left is our motherboard, which uses an ESP32 microcontroller to control the whole system. Primarily, it's interfacing 6 DC dynamical motors, 6 servo motors, 2 solenoid valves, and 1 pressure transducer. Then in the top row, within that figure, you can see a series of dedicated drivers, which are making sure that we're delivering sufficient power to our motors and solenoid valves. And then finally, towards the right, we have our power distribution board, which uses a circuit breaker and fuse for safety. Overall, the system is powered using a lithium polymer battery. In terms of software, the system employs a state machine routine, which allows us to cycle through the various states we want the system to be in, such as anchor deployment, TARP inflation, deflation, as well as states that allow us to reset the system. Lastly, the software also implemented a web server as a user interface, which allowed us to wirelessly control the system using the 802.11 Wi-Fi standard, which was also used in the CLIPS lander as a standard communication protocol.
With the subsystems of AEGIS understood and manufactured, we can enter into our relevant environment testing. Relevant environment Test, beautiful. Our testing was planned out through a comprehensive testing plan at the project's onset. This incorporated defining tests to validate all systems of AEGIS up to TRL5. These testing required 20 separate test articles to be made, and we will begin going through these tests. So our first one is our inflated beam structural tests. So the inflated beam judges that has been passed around is a 12.7 centimeter diameter inflated beam by 20 centimeters long. It's constructed out of a ballistic nylon inner layer and encased in a stitched Kevlar sheath. The first test performed on this was compressive testing to validate the beam's ability to withstand either a lander's leg or a rover's wheel applying direct compressive force. The loading was performed up to 98 kilopascals and tested at both an internal pressure of 137 and an internal pressure of 172 kPa. Through this testing, the internal and external pressures were able to equalize with no unintended deformation or kinking, and as such, this test was considered a success. Second test that was performed on these beams was 3-point bend testing, which evaluated the critical kinking characteristics which could be involved in gas deflection. The setup on the right here is simulating the upper beam being pulled down on a deflector spoke during landing procedures. And it was able to be loaded up to 640 newtons without any critical kinking permeating past the loading zone, which is then considered a successful test. Evaluating the TARP, we can go into our TARP structural testing. So this test was performed on multiple different TARP stack-ups, and you can see on the left here a time-lapse of our compression mounting plate testing, which is the full stack-up utilizing compression mounting plates to simulate how the enclosure would be affixed to the TARP. As you can see from the graph on the right, we found that the alumina felt failed first, followed by the aluminized kapton, and then the knit carbon fiber proceeding to unravel. These tests are integral in considering the material as a single stack-up for future analysis to evaluate its structural integrity during landing operations.
The thermal ablative test was used to perform and test the thermal degradation of the TARP in the heat shield using an oxyacetylene torch with an argon flood to reduce oxidation of the materials. Both the TARP and the heat shield use materials with characteristics of being able to withstand extremely high temperatures, materials like the carbon fiber and the RVC foam. The results show that their zirconia paint and their zirconia plasma coating provide extreme protection against high temperatures. The gas permeability test was performed to observe how the TARP handles external gases, like the rocket exhaust, that are attempting to penetrate the inflatable. Using a test stand that was built in-house, the results show that with and without the aluminized kapton, the TARP is able to provide the necessary shielding against these foreign gases. And on the left, we have the abrasion testing, which was performed to test the durability of the TARP against its environment, as in against the regolith. The results show that a mean time to failure was 0.91 meters. And on the right, we have the fabric stiffness test, which was performed to evaluate the tarp's flexibility and its suitability to be stowed in a compact configuration. The results show that the materials used were flexible, and a desired flexibility can also be achieved through stitching.
3 tests were performed on the anchors: deployment, vertical, and lateral pullout. For the lateral pullout test, the ASTM standards for helical pile testing were used to inspire the procedures. With the vertical testing, the 2 tips to the augers were designed, helical and wood screw. The helical design consists of a single blade at the tip of the auger, and a wood screw design has a sharper penetrating cone and more threads. The helical design has a greater vertical pullout, but has a lower deployment, going only 1/3 of the deployment length, compared to the wood screw design, which has a 2/3 deployment length and a slightly lower vertical pullout resistance. This confirmed our individual bearing model that was used to drive the critical dimension. For the lateral testing, a test apparatus was manufactured for the wood screw test to create a more realistic failure case and where the augers would slide rather than rotating and pivoting.
So the validation of the electronics and controls took place in a series of isolated steps, each step representing a unique process in the overall deployment of the AEGIS package. So starting towards our left, you can see us testing our anchors. These anchors were driven using DC dynamic slow motors, which are specialized continuous servo motors. These motors were used because of their ability to precisely achieve and maintain a given position. And this precision was important because it allowed us to define and measure how deep our anchors had dug in. Then coming towards the center, you can see us testing our tarp release mechanism, which is essentially 6 servos cycling from 0 to 60 degrees to unlock the AEGIS package. And finally, towards the right, you can see us that testing was also performed to make sure that our pressure controller was able to maintain a given pressure set point during tarp inflation. The setup over here shows an input from the air compressor, a relay to control the solenoid valve, a pressure transducer for feedback, and a microcontroller. A bank control methodology was employed in software given the binary nature of our solenoid valve actuator, and a low-frequency control loop was established to avoid hysteresis. Overall, our controller was able to maintain within 1.7 kilopascals of the pressure set point.
So analog earth testing was conducted to validate AEGIS in 2 key aspects: its ability to deflect exhaust gases and its successful deployment ability. This test takes AEGIS to TRL 5, demonstrating its capability in relevant environmental conditions. This test was conducted at Friends of Amateur Rocketry in Mojave Desert in California to analyze the flow of exhaust gases off of AEGIS without being in contact with the ground. We fabricated a custom-made boom to hold the motor in place, which was fixed at 1 meter above the heat shield. We used an Aerotech Level 3 solid plug motor, which produced thrust of 1.4 kilonewtons and had a burn time of 7.2 seconds, with peak temperature reaching 1,198 degrees Celsius. We were successful in deflecting the exhaust gases for the first 4 seconds of the ignition. In this clip, we see the rocket fire test that was captured using multiple GoPro cameras and a DJI drone with thermal imaging. Thermal imaging helps us to analyze the flow of exhaust gases and track heat distribution on AEGIS.
Awesome. And following a rather explosive test environment in the rocket fire testing, we moved on to our full system deployment. This was conducted at SP Crater just north of Flagstaff, Arizona. SP Crater was selected due to its heritage as an analogous lunar environment, given the volcanic sediment, which is a relevant environment for the lunar terrain. After location was set and selected for minor debris and minimum foliage, initial system characterization began, where we evaluated each of AEGIS' subsystems before moving on to full deployment. We'll see now, starting at the spring-loaded deployment, as we actuate our exterior panels. Once these are actuated, the inner tarp and skeleton are revealed, and inflation is ready to begin. An external compressor was used to increase safety on site, as well as consistency to provide all of the high-pressure gases. And you can see as the system inflates, slowly the tarp and inflated skeleton progress outside of their initial bounds. You can see a major advantage of these inflated systems being their compliance to minor perturbations, whether it be small debris on the ground or the enclosure panels maybe not going up all the way. The system is still able to accommodate the various constraints and deploy to its final state. Through repeated testing, it was found that compressing the tarp and skeleton in an accordion-like manner resulted in the smoothest deployment to its full scale. Overall, this test was a market success, being repeated 4 separate times of successful deployment. A final deployment time of 76 seconds was achieved with resilience to minor debris, and it was also able to be deployed at an incline. This test marks AEGIS's progression to TRL 5, and it moves us into our path to flight.
To continue AEGIS past TRL 5, the next steps would be to do a full systems test in relevant environments. This would include building a full-scale model, since our model is currently at 1/5 scale. We would add the communication system that is necessary for landers to center onto the pad. We would add in a thermal control system, as well as improve the structural integrity of the pad. To achieve a TRL level of 7 and 8, we would first replace all components with a heritage or flight-ready component. This includes the pressure vessels, battery, motors and actuators, and all of the electronics. This prototype could be qualified by sending it aboard a CLIPS mission to the moon to serve as a demonstration of both deployment and lander testing. In addition to deployment testing, AEGIS will need to pass TVAC testing, vibration testing, and dust ingress testing. To continue AEGIS along the path to flight, our team is planning on using any remaining funds, as well as pursuing additional grant opportunities such as NASA tech flights to continue working towards TRL 6.
Overall, we are incredibly proud of AEGIS and how far the team has come, and we thank you for taking your time out of your day to listen to us. And a special thanks out to our faculty, and as well as the NASA Big Idea coordinators for making this all happen. Thank you very much.
Excellent job, Arizona State. Let's open the Q&A session with the judges, starting with Doug.
All right, great job, you guys. I think everybody is impressed with the thermal GoPro cameras or the thermal drone cameras. I don't know where you got those, but we'd like to use them. So very cool testing. So my question is sort of related to that. With the rocket testing that you did, specific to the anchors, did you use this is not it, but did you use the flight anchors for that test? And then how did you anchor it? And then my second part of a similar question is, when you did the actual deployment test in the field, did you have the flight anchors there? And then did you do any sort of testing on it to show that they were, in the ground?
Yeah, so with the rocket fire testing, no hardware was inside of the enclosure. It was just like the geometry, the shape that was tested. For manufacturing of the anchors, we only used PLA with 3D printing, just due to cost and due to the rapid changing method. But for the deployment testing, we used a 1/5 scale model that we developed for testing, and we did a kind of an informal, just pushing it laterally and seeing it. It was pretty good, so it was nice. Does that answer the question? Awesome.
What kind of landers you designed the system for?
Say that again?
What kind of landers?
Yeah, so this was designed for CLIPS landers such as the Astrobotics Griffin. So it was designed to be both delivered by that, and all the dimensions and CFD analysis was based off the Griffin.
You have any idea how difficult it will be to scale up to the next level of landers?
Yes, that's something we'd love to look into further. The actual design process for that opens that to be a very easy process. Of a lot of ways that we were able to optimize was just based off of the diameter of the beams and the actual total pad radius, and that gave us a lot of control over the critical moments induced in the beams, as well as gas flow redirection.
Thank you. Great job.
That outer ring, if I understand it correctly, that once it deploys, that outer ring does need to re-inflate and deflate for every landing.
Correct.
Did you take a look if that thing won't inflate a second time or something like that? Do you still achieve some measure of dust protection?
Yeah, so from our preliminary CFD analysis, we got with the deflectors up, it was a 95% increase or decrease in fluid shear stress. With the deflectors down, it was still roughly a 55% decrease. So still significant savings from full rocket blast.
On the outer ring, what determined the diameter of that as far as the minor diameter of the torus on that? Did you guys do analysis on kind of the bending and kind of, did you do any testing on that to kind of determine what pressure and what diameter you needed on that outer ring?
Yeah, so all that design was driven through some papers that we found at the beginning of the project, which characterize the various different kinking moments that occur in inflated beams. The testing that we were able to get access to was that 3-point bend testing. We would like to further analyze more failure modes at different locations through more established and a wider variety of tests.
Throw along a little bit of a systems engineering question. You know, validation is, are you building the right thing? And verification, does the thing you build do what it's supposed to? So did you contact any of the launch providers and say, hey, we've got this, is the pad big enough based on nominal landing accuracies if we have a beacon, and is the vertical offset, you know, not going to interfere anything? So if you didn't talk to the providers, you said something about clips, but how did you do that validation?
Yeah, so our validation was using any documentation we could find from Astrobotics on their Griffin lander for its various dimensions, thrust, the size of its landing legs to make sure those could encompass the central enclosure without getting hooked up while landing.
I might miss, but do you have the image of your TARP and landing pad structure after half-fire the test? Doing some damage after some fire?
After the rocket fire testing? Yeah, so. Do you want to take that?
Yeah. So for the last, as I mentioned, that we were successful in deflecting the gases for the first 4 seconds of the ignition. But when coming down to the last 3 seconds of the ignition, we faced unplanned rapid disassembly of our prototype. So we did collect the data and the debris that we were left with of our prototype. And yeah, we do have pictures with us right now, but we didn't put it up on our presentation for at the moment. But yes, it was because of the motor that we had used. It was a bit of, it was more powerful than what we expected. As mentioned previously, rocket science is fun, but it's hard as well. So, yeah.
Yeah, so if you'd like, we can get you all those pictures from the post-test to show off.
All right. Let's see. Oh yeah, so you had a question in your paper, or not a question, you had a picture in your paper and another picture in here of the lander actually landed on your pad, and it looked like the one in the paper, it kind of looked like the feet were almost in between the pedals that are deployed, and then the one you showed in this, it looks like the lander's a lot bigger, where it wasn't interfering. So how much did you guys look at, you know, obviously you had one lander in mind to land the thing, but in terms of other landers, because there's quite a range of, you know, small clips landers out there, is it adaptable or applicable to those as well? Or is it very specific to one that has, you know, a certain sized rocket in between it and the legs have to be a certain diameter so it doesn't interfere with your panels?
Cycle all the way back here. Right. Let me give you, I'll stay on this one. So yes, the design is open to a variety of different landers. The main driving factors were this, the outer inflated diameter, that was driven based off of the power of the rocket. So we needed that to be large enough such that the pressures applied there would not kink the beams. However, the internal enclosure and the central heat shield was spec'd based off of the size of the rocket plume based off of our CFD analysis. So that was that was the one material that we could ensure would be resilient at those high temperatures and forces. So we scaled that up. However, a lot of our testing shows that we can possibly reduce that, which would reduce the entire size of the enclosure and the whole system's sewed volume. So that could be dependent on different landers, depending on their size of their rocket. That would drive that major dimension.
So, and please correct me if I'm wrong, the goal of this, as it looks right now, is fully deployed on the lunar surface. And then somehow it comes back into the enclosure? Or do you just leave it like this on the lunar surface?
Yeah, so this would be its fully deployed state. The system never goes back into its closure. So the idea is then to get different landers and their payloads in and out. The outer ring or the upper ring, through deflation, would be able to fall down. You can cycle all of your resources, your payloads out, and then it could reinflate for that lander to take off and another one to arrive. But the system itself does not package itself back up.
So there's no mechanisms that are coming in and out once it's deployed on
Correct.
the surface?
After its first actuation, the only things that move are its upper wall.
Got it. I guess how deep does the anchor need to go on the lunar surface?
So from our calculations, we calculated a critical depth of, I think, 0.42 meters with a diameter of 0.083 centimeters. Or not centimeters, sorry, meters. And that was driven by the failure case. So it's kind of difficult, and it's difficult for me to understand still, but there are different methods of failuring where you have, basically, you can have an entire cylinder, and that's like that goes up with it. That's a deep embedment, like deep anchoring. And then you have another one case where it's just individual bearing method, and that's when you have a more shallow anchor, and that's when say you have like multiple threads, the dirt or the regolith stays between the threads, and it kind of like comes up in sections. And then you have shallow anchoring, and that's when you have, if you can imagine, a cone on top of the top plate or the blade, and that cone's weight is what keeps the anchor, like that's what gives it its resistive force. And that was confirmed with our modeling. I used MATLAB to implement the 3 different types, and from our imperial data, we were able to match it to the shallow anchoring. So how much that cone weighs is how much anchoring you're gonna get. And the deeper you go, the deeper and the better it gets, exponentially.
What type of, I'm sorry, can I ask another? Sorry. What type of terrain are you assuming this anchor is gonna work on? Because if you look at a cross-section of the lunar surface, you have that upper layer that's dusty, then you have regolith, but you have also glutinous rocks, it can be glassy. So did you take that into consideration in the design of your anchor?
Yes, we did. So the regolith is actually like the very top, which is like super powdery, is actually really deep. And you don't need to go like more than, I would say, 2 to 3 meters for like some really good, like, if you get deep anchoring, you can get exponential, like a kilonewton, just going by about 3 meters deep. And you start to get into more rocky terrain, I think, from what I remember from reading the Lunar source book. Don't quote me on this, though. If you want more of an answer, go to Lunar source book. Don't take me. But then you start to get more into rocky terrain, and you can get sufficient anchoring at the higher levels.
Thank you.
Yeah, just real quick along those lines was weight on bit, and whether it's going to basically lift your platform up on the lunar surface with much less mass. And so maybe, like she brought up, I think her concern was, in different terrain, is it just going to lift your platform up and not sink them in?
Yeah, and kind of on top of that, our critical failure modes were mainly for lateral displacement. Right, you have the full force of the rocket coming down from our CFD simulations. We weren't seeing much actual vertical translation. So our critical loads that we were trying to design for was that lateral displacement to make sure the landing pad is not shifting out of the way and getting displaced during the landing.
We still have a lot of time left on this team's clock. So do we have any other questions from the judging panel?
I do. So I'm an environments person, so this question is probably what I'll ask everybody. What other environments on the lunar surface have you not considered in your test? And how do you plan to either mitigate to those with design, or are you already not susceptible to those environments in your design?
Yeah, so our initial design is for, like you were mentioning before, our anchoring system would be purely into regolith, and that fine grain regolith. And the rest of the environments that we've considered are, we would like to look more into, like you mentioned before, the micrometeors, having considerations for those and testing for the impact resistance of our inflated members. Yeah, so we'd like to expand our testing further into a wider variety of environments to make this more applicable across a wide variety.
Any other questions?
Yeah, I'll just ask one. You know, a lot of it is you want to unload payloads, and so you can deflate and stuff. Now the whatever systems are unloading payloads will probably have grousers and things on those that are not very friendly to, and especially the material layup that you have. Have you sort of looked at the material, how it would hold up with wheels rolling over it?
Yeah, so the extent that we tested currently was simply the compression testing, so just that direct force. However, we would like to further evaluate that with a more rigorous setup involving, having treads or wheels rolling over that to see how that would interface, as well as seeing that in a regolith environment instead of just the like singular tensile loading of our test machines.
Doug, I think.
As far as your system, obviously you're going to deflate, you're going to reinflate. How many times do you think, are you guys predicting, or what did you design for as far as how many cycles, how many landings do you think the system will survive? And then along with that, how are you inflating and deflating? Is it completely a storage system, or are you reclaiming and putting back in? What's your approach for that?
Yeah, so for the reinflation cycle, the compressed gas we have spec'd out for initial inflation as well as 20 reinflation cycles. And as far as how that reinflation works, that is just let out to the environment, hence why we really wanted to involve those check valves, because that cuts the reinflation cost by about 4 times. So it expands a lot more, you can get a lot more use out of it. Similar to what Caltech was talking about, we'd also like to further our testing for the actual materials themselves to see their degradation over time for that repeated use, but the system has been designed preliminary for those like 20 reinflation cycles.
And the leak rate, did you guys do any research on that, or kind of assume any sort of a leak rate in those calculations?
No, we did not. We would, definitely like to start incorporating that, especially given some of the other test results, seeing some wear and tear there. That would be something to evaluate how effective the tarp encompassing the inflated beams is at preventing those abrasive particles from interacting. Yeah.
I just had a follow on that, just because it's kind of similar. Sorry, Doug. Which was, did you look at kind of a partial deflation, so just deflating like one segment of it to drive something out of it, or do you have to do the entire thing when you're deflating?
Yeah, so the way the system is currently constructed, it is full deflation, and that would just be from, just those linear deflector spokes. However, that is something that we could start splitting this into different volumes. The main thing with that is what we learned with all of the inflatables manufacturers that we work with. Every joint is another cause for leak. So this was our most simplified way at creating the least amount of volumes without the cost of an insane amount of compressed gas. So this is kind of how we approach that.
It's like you need to add more pneumatics and more electronics to control that system, so then there's the power requirement you need to consider. So that was another factor. Yeah.
Anybody but Doug. I'm just kidding. Doug, go for it.
I'll wait. So this is a really good engineering project, right? Like just like in real life, we have a budget and you have to do testing, and you can only do so much with the money you have. So theoretically, if you had a bunch more money leaving here today, what do you feel is like the biggest gap that you'd like to spend that money on and do next as the next thing to validate this?
Yeah, I think what we would definitely want to do is get back out to FAR. After that testing, we were experiencing a few constraints with the model that was used. So its initial internal PSI, the final model that we used for that could not achieve that. So we would like to go back, get some more rigorous materials for that, get more unified construction to redo that test with more accurate parameters for that. And that would involve, a lot of money and time to facilitate that whole inflated system.
Malena.
Can you comment on that carbon foam that you selected? And I'm very happy you based it off of PSP. But was it hard to work with? Did it particulate a lot? Just wondering about foam because foam is my arch nemesis as a materials and contamination control person. So yeah, could you comment a little bit on the foam?
Talk about that, because you manufactured that.
Yeah, so funny enough, I was the one that manufactured it. And yes, it did. It did make particles. We cut it on a bandsaw, and we wore respirators, and then we had a shop vac connected, and then we shot back the thing, and then, yep, that was our mitigation.
Wait, so it was messy, and then how did you
We
clean
used
it
a
up?
shop vac with a HIPAA filter to be able to capture the particles.
All right, thank you.
What kind of temperature this heat shield can withstand?
Yeah, so as we mentioned, the RVC foam itself has an operational ceiling of 3,500 degrees Celsius, and the zirconia coating and carbon fiber in a non-oxidizing environment also reach that same temperature. And this is all spec'd based off of, again, the Griffin lander, which we anticipated temperatures of around 3,000 Kelvin. So all of these are sufficient for that case.
Ryan, you have a question?
So with in the images for your prototypes, the outer ring was kind of up and down a little bit. And so it seems like probably the pressure that you couldn't achieve and different understanding of the loads. But in the end, in the thermal camera, the system seemed to work really well. Did it seem like with the blast, it was actually putting the wall up in place because of the flow, or what did you expect it to perform as well based on the position of that outer wall?
Yeah, so in some of our initial design work, that was actually a plus going into that was, right, once you start putting that all in tension, just the geometry of it, one inspiration for that was just how even skirts are sewn together, it kind of locks the conal shape of it as you start putting it in tension. So that was a big plus that we got to see, as well. Seeing the prototype manufactured by Bestway with more rigid connection points was also better at kind of maintaining that initial shape. But yeah, the rocket fire testing definitely had a helping hand in getting all of that plume redirected upwards.
And did you do any rocket fire? You mentioned you looked at it kind of with that outer ring inflated. Did you do any rocket fire testing actually with that, or was it just simulation?
That was just simulation. So we'd like to go back and actually evaluate that with that failure mode. But for the test article that we took out there, it was sufficient for the first test. And we'd like to go back for a second.
Because I'd be curious to see how much do you need that inflated? Would it actually pull itself up and even function better than your simulation?
Yeah, which would be really exciting because that was actually one of the first ideas we had was having those walls pop up that we almost included in the proposal and thought that was a little bit of a safer option. But yeah, it's a cool thought.
Any other judge?
How much margin do you have for landing error? I mean, if your lander's half a meter to the side, or is it going to burn through the skirt then? Or?
Yeah, so currently it was designed, all of the design work was based off of that direct vertical landing. However, based off of, or the main constraint for broadening that zone was the thermal and structural ability of the tarp stack-up, which through, you can see the test article there, that with just a painted zirconia coating, we were still able to get, we did test it to failure, but we were still able to get thermal resiliency during that test, which would lead to our ability to shrink the center enclosure, so that center heat shield should offer up more space and open it up. Currently, it was designed for direct central landing, but it has a margin of about half a meter to the left or right.
Melina?
Can you comment a bit on challenges during your project management, budget management, just in general? I do see you guys were very cohesive presenting. It's very nice to see that in your team.
Yeah, as far as kind of the project as a whole, management-wise, like a lot of the people you see up here got brought on after the proposal. So that was definitely interesting getting kind of exactly like what Caltech was saying. Like you get a lot of different brains, but that also means a lot of different brains. So actually transferring all that over was definitely a challenge, but it did open up for a wide array of skill sets, which was very exciting. And as far as like cost, there was a lot of, it was an interesting challenge to like weigh how accurate we can get our test articles to go while still being and working within budget. So getting those, finding cheaper alternatives to simulate the same materials or test setups. There's a lot of that, especially with the inflated beams. Turns out those get really expensive when they're super custom. But being able to modify some already manufactured things really was able to cut costs and open us up to buy more expensive and invest more time in other areas, such as the full inflated system.
And any other burning questions from the judges? Jinho.
What kind of the carbon fiber did you use for this study? Do you remember, is it like some regular carbon fiber or some pitch carbon fiber?
Yeah, so this was a carbon-carbon composite that we should have more details in the technical paper that we can talk about after. I don't know exactly off the top of my head the specifications for it, but it was the construction of it is different from more epoxy-based carbon fibers because it opens up to a higher temperature ceiling, which is why we selected one with a far lower epoxy percentage.
I mean the carbon fiber fabric, the tarp.
Oh, the tarp? Yeah. So that was a jersey knit carbon fiber, which, yeah, in one of those baggies, you got a little section of that. And again, same thing, I don't have the exact details on like its full like properties and weave, but we can totally get you access to that from the documentation that we got.
Yeah, the reason I'm asking is you can find some high thermally conductive carbon fiber. It's pitch based. That might be better choice for your application because you need more higher thermal conductivity too.
Yeah.
So yeah, distribute the thermal energy.
Good. We will totally look into that for further testing. Thank you.
3 minutes on the clock. Any other questions?
What about micrometeorite damage? How would you mitigate that? Or are you hoping that your TARP system is going to help with that?
Yeah, so the approach for that would be further testing into the TARP system. There are about 5 layers of materials in between from the outside of the TARP to the actual inflated member itself. So doing further testing with that and also incorporating, we can add additional layers there. A nice thing about the TARP stack of itself is it is modular for the different zones. So for example, we are most concerned about the air permeability at the deflector spokes. So that luminized Kapton could be replaced with other different fabrics to make that more structurally rigid or less permeable to those micrometeorites. But yeah, we would like to do further testing on that.
Anything else from the judging panel? All right, then for the first time today, we will open up questions to the audience. Are there any questions from anyone in the audience? Everyone wants to go to lunch. All right, oh, we got one. Here, I'll give you the mic so you can speak into the mic.
So how do you, your FAR test lasted for 4 seconds. How do you scale survival time with your heat shield? What's your plan on getting a better survival time?
Yeah, so for progressing that survivability, the failure mode that we saw was the way that the heat shield was mounted to the enclosure left itself, the center was able to basically crack open. and the gases are able to flood in and then expand out. So improving that and giving more supports inside of that structure will help immensely with that. And then even more so, getting more developed components higher PSI, that will help with the external components also being rigid during rocket fire testing.
45 seconds left. Anybody else? All right. Oh, quick.
Just a small sizing question. In this, what is the diameter of the wrapped up enclosure?
The diameter of the tarp or the enclosure as a whole?
Of this, what I'm seeing.
Yeah, so at the full scale, this is 4 meters in diameter. Yeah.
And then let's go ahead and give a round of applause for Arizona State.